just to sort of separate. And let me remind you that the last thing that we were discussing last time was log concave functions and measures. So a function is called log concave if the logarithm is concave, or if this inequality holds for any pair of points x and y in the domain of the function. All the domains, as we discussed, are on Rn. A measure is called log concave if this inequality, which is sort of analogous to Minkowski inequality, holds. That's when a measure is called log concave. And Borel's theorem, Borel here with 2L, sorry. Christer Borel from Swiss, tells us that a measure is log concave if and only if it has a density, or perhaps on some affine subspace rather than a full space, and the density is a log concave function. And so we discussed that Borel's theorem implies Minkowski inequality. Right, let's return to this again. So Borel theorem implies Minkowski inequality. So indeed, what is the density of the back measure? Can somebody tell me?
Yeah, so it's just the identity.
Yeah, so the density is just 1. So, sorry. Clearly f is a log concave function, right? So constant is a log concave function. Of course, right? You can say that, yeah. 1 is e to the power minus 0, and 0 is a convex function. And so by Borel's theorem, Lebesgue measure satisfies the Minkowski inequality. So Minkowski. So yeah, so this means that Borel's theorem is actually more general, and we will prove it today. So some other examples. Just 1 second. I don't understand why my pencil continues to not work all the time. Is a Gaussian measure. So this is a classical example that we will discuss hopefully with you. So the Gaussian measure d gamma is a probability measure which has density e to the power minus Lebesgue length x squared over 2 with some normalizing constant, and this normalizing constant is 2 pi to the power minus n over 2 dx. So the Gaussian measure, it has sort of a cap like this. And it's also a log concave measure because the density f of x e to the power minus x squared over 2 times cn is, so it equals to e to the power minus v, where v of x is, this is how I like to think about it, x squared plus some as a constant. And of course, this is a convex function. So it's e to the power minus convex function. I mean, this is roughly how it looks. Convex also satisfies Minkowski. So Gaussian measure of lambda k plus 1 minus lambda L is bigger than or equal to Gaussian measure of k to the power lambda, Gaussian measure of L to the power 1 minus lambda. It tells something about probability, so it's about normal distribution, which is very useful in probability theory. So this is a little bit of a connection across fields here. Are there any questions? Everyone's a bit quieter today. Let me see if I don't know if I can see anybody's faces here. Yes, does this make sense?
Yes.
Great. So we will prove this Borel's theorem, and the way we will prove it is we will prove the cornerstone of convexity, really, the most general inequality, more general than Minkowski, called Prokop-Lendler inequality. So here is an important theorem. Prokop-Lendler that says that if lambda is between 0 and 1, and we have three functions f, g, and h on Rn into R, such that integral of e to the power minus f, integral of e to the power minus g, and integral of e to the power minus h all exist. And also, of course, measurable. All the functions we consider will be measurable for sure. So suppose we have three such functions, such that for any x and y in Rn, we have h of lambda x, and also for any lambda between the fixed lambda here, h of lambda x plus 1 minus lambda y is smaller than or equal to lambda f of x plus 1 minus lambda g of y. Suppose we have a triplet of functions with this property. Then one can also compare integrals in a way that's sort of reverse Hölder inequality. Integral of e to the power minus h on Rn is bigger than or equal to integral of e to the power minus f to the power lambda times integral of e to the power minus g to the power 1 minus lambda. So this is Prokop-Lendler's inequality. Are there any questions about it? So it tells us that if you have a triplet of functions that satisfy some property, then the integrals can also be compared in this way. So can somebody explain to me why does Prokop-Lendler inequality imply Borel's theorem that we just discussed and therefore Minkowski?
If H is convex, then we can substitute for F and G H, and the inequality would still hold. And if e to the power of minus e h would be the density, then it would
Exactly.
imply the theorem.
Exactly. Exactly. So let us do the following change. So we have dmu is a measure with density f of x dx. So this is a measure with density f, and we know that f is log concave. So suppose this is something that we know. So let's consider e to the power minus h of x to be, let's do e to the power minus h, but we have a bit of an intersection of notation. Sorry, so we have the density, for the sake of this argument, let's make the density phi, if that's okay. So let's say the density phi is a log concave function in order to not cross wires here. So we need to correspond these three functions f, g, and h to the density. So suppose e to the power minus f is phi of x times the characteristic function of the set k. So we have sets. By the way, I wanted to bring your attention that there was a typo in the homework that somebody brought up to my attention. Thank you very much. If you have a pair of Borel measurable sets, the Minkowski sum is not necessarily Borel measurable, but it is necessarily back measurable. So if you have a pair of Borel measurable sets, that's what we consider here, K and L, e to the power minus g is phi of x fraction of L. H, we take phi of x times their Minkowski average. Times, sorry, the characteristic function of the Minkowski average. Then what do we note? That the log concavity of f of phi implies that h of lambda x plus 1 minus lambda y to lambda f of x plus 1 minus lambda g of y due to log concavity of phi. Right? Do you agree? I don't want to write it in great detail, but you can have a look at this. So therefore, Prokop's condition is satisfied. And from here, you get that integral of e to the power minus h is bigger than integral of e to the power minus phi to the power lambda. Integral of e to the power minus g to the power 1 minus lambda. Or in other words, integral of lambda k plus 1 minus lambda L of phi is bigger than or equal to this, or precisely what we were looking for. We deduce the log concavity of the measure mu. This is a difficult direction of the theorem. Of course, there is some additional details, but pretty much the key part of Borel's theorem follows from Pircopa-Landler inequality automatically. So Pircopa-Landler inequality indeed is this thing that's called the functional version of Minkowski inequality. And that's what we will prove now. Are there any questions? Let me give you actually just 1 second. I need to figure out what's going on here now. Good, I'm back. So does anyone have any questions? I just had some very loud noise from the streets that I had to close the window. So before I start proving it. So precomplement inequality, actually the proof is fairly simple and goes by induction. Let's switch to this color now. Proof of the precomplement inequality. So the proof goes by induction in dimension. Let us recall something that's called the layer cake formula, which is what we will need now, the layer cake formula that's generally very useful in analysis. If you integrate in a function with respect to a measure, a function is non-negative on a Rn, you can write it as integral from 0 to infinity mu of the set of points x in Rn such that f of x is bigger than t. So this is a function on t dt. Are you guys familiar with this fact from probability essentially?
Yes.
Can anybody remind me how to prove this?
Frobenius theorem.
So Frobenius theorem, yes, exactly. So integral of f, generally we think of it as something like this, right? So this is what you see on the right, but what you see here on the left, in a way you can view as measuring the area in these horizontal lines, right? That's precisely what you have here, right? So this is one of those classical facts. So this is something that we will use. Let us change the notation a bit. Let's a slight swap of notation. So capital F of x is e to the power minus little f of x. Capital G of x is e to the power minus little g of x. Capital H. So the condition of Precopa that I really prefer to write in this form for a reason you will see, but often people only use the notation of those capital letters that you will see in a minute as well. So this condition of Precopa becomes h of lambda x plus 1 minus lambda y is bigger than or equal to f of x to the power lambda, g of y to the power 1 minus lambda. So this is the condition about functions that we have, right? And we want to show that integral of h is bigger than or equal to integral of, so it's the same thing you can write about integrals. Okay, so let's do base of induction, dimension 1. So we have these three functions. Notice by definition, they're all non-negative. Integral of h on R using the layer cake formula that we now reviewed. You can write as integral from 0 to infinity of the length of the set, of the linear set T in R such that h of t is bigger than s ds, for example. This is how you can write integral of h. So we want to compare it to integrals of f and g. And so the cool thing here is that this inequality gives some containment about level sets. So this is like a little logical exercise to verify that what's written here implies what's written here, right? Because if you consider a point t such that f of t is bigger than s and g of t is bigger than s, then this point is in both of these sets on the right, and then by this inequality, it's also in the point on the left. And yeah, it's a like little logical exercise, very small, that I will probably not dwell on, if that's okay. Does this make sense?
Yeah.
So because yes.
Yes.
Great. So because of this, I can say that this is bigger than or equal to integral from 0 to infinity of lambda times the measure of the set f bigger than s plus 1 minus lambda times the measure of the set g bigger than s ds. Right? This plus stands for one-dimensional Minkowski sum, which is not a very complicated thing. So very good, which you can write back like this. And using the layer cake formula again, you get lambda integral of f plus 1 minus lambda integral of g on R. Agreed? And using the little inequality for numbers that we discussed before with you, right? The inequality was that lambda a plus 1 minus lambda b, if a and b are non-negative, is bigger than or equal to a to the power lambda b to the power minus 1 minus lambda, right? So I can say that this is bigger than or equal to integral of f on R to the power lambda, integral on R of g to the power 1 minus lambda. Right, so we verified the base of induction. Base of induction is verified. We do have the inequality integral of h. This inequality is bigger than integral of f to the power lambda, integral of g to the power 1 minus lambda. So in dimension 1, it's really very straightforward. Any questions about this? So now let's move to the induction. Step 2, induction. Suppose the Prekoppel-Endler theorem is verified in dimension Rn minus 1. We will verify it in Rn. So let's consider the function with an index n, hn, depending on the last coordinate of xn. So x, we write vector in Rn, we write it as a vector of coordinates. And it's integral over Rn minus 1 of my function h in the first n minus 1 coordinates. So I integrate the functions that depend on n coordinates in n minus 1 coordinates, so I'm left with a function that depends on this one last coordinate. Does this make sense? So
Yes.
x is x1. Great. xn, I will also use notation x bar xn. Now, similarly, same way you can define, of course, functions Fn and Gn. I'm not gonna write it in exact same way. So we have that H of lambda x bar xn plus 1 minus lambda y bar yn is bigger than or equal to f of lambda x bar xn to the power, so f of x bar xn to the power lambda times g of x y bar yn to the power 1 minus lambda. Do you agree? Right, so can somebody remind me, explain to me, why do we have this? We have by the right, what theorem are we proving?
Isn't it by the induction hypothesis?
No, it's by the assumption. It's by the assumption of the theorem, right? It's by the assumption of Prekopa-Lendler about H, F, and G. But now you're absolutely right. You're absolutely right. It's time to use the induction hypothesis that tells you that in Rn minus 1, Prekopa holds. So induction hypothesis, which is an inequality about integrals, right? It tells you that on Rn minus 1, it holds. Prekopa holds, Prekopa-Lendler holds, meaning that integral of h on Rn minus 1 is bigger than or equal to, because of this assumption, of f integral of g, all of this on Rn minus 1, or in our notation, hn of lambda xn plus 1 minus lambda yn is going to be bigger than or equal to fn of xn to the power lambda times g n of x of yn to the power 1 minus lambda. Right, and this is something about one-dimensional functions, right? So this is one-dimensional functions. So what can we use now?
One-dimensional case of this inequality.
Mm-hmm. Exactly. Therefore, so by step 1, we have integral of hn bigger than or equal to integral of fn to the power lambda, integral of jn to the power 1 minus lambda. But if I integrate these functions that I defined like this in this one more coordinate, I just get integral of h, integral of f, and integral of g correspondingly, which is exactly what we wanted to prove. It's a word, as I said, Prekopa-Lendler inequality. As a consequence, we didn't just prove Prekopa-Lendler inequality. You see, we also proved Minkowski inequality. We proved Borel's theorem, Godlow-Concave measures. So thus, the Minkowski inequality is now also proven. And therefore, the isoperimetric inequality. All as promised. So right now, everything is at least done. Are there any questions about anything? Let me now make a pause. We finished proving this Prekopa. Enter. Let me. This was part 1. Does anyone have any questions? Actually, maybe a quick remark. I'm not gonna spend time on this, but in the notes you can have a look also. There's a more general, so Prekopa-Landler is actually Prekopa-Landler inequality, in fact, is a member of a larger family of inequalities. Called Borel-Braskamp-Leib inequality. I will not spend time on it now, but those who are interested could have a look in the notes. Maybe Stephanie will also discuss it in the in the practice sessions. Cool. Any questions, anyone? Let me try and have a look on Zoom. It's a bit not ideal to just be the only one who's talking.
Everything is clear.
Let's see if anyone's willing to say anything. Cool. So let's move on and let's try and see Prekopa-Landler inequality actually as something that we saw in Brun-Minkowski inequality, in that it is a cavity principle. So here is our kind of main idea from concavity principles. To isoperimetry. Linearizations. What do I want to explain about this? So in general, suppose there is a concave function. Suppose f is some functional. We'll consider functionals, right? Suppose AF is a functional such that for any pair of elements of linear space that it's defined on F and G, 1 minus t for any t between 0 and 1, f plus t, g is bigger than or equal to 1 minus t, f of f plus t f of g. i.e. f is concave. So we have a functional such that if you have here f and g, and you have this midpoint, the value of the functional at the midpoint is bigger than the average of the values of the functional. So f is a concave functional on some space. Define function alpha of t, which is f 1 minus t f plus t g minus 1 minus t f of f minus t, just a second, let me shift it a bit. F of g. What can I say about this function? So this clearly, what I said, alpha of t is always non-negative on our interval 0, 1. What can we also say? We can also clearly say that what is the value of alpha at 0?
0.
It's 0, exactly. Function that is 0, 0, and is somehow non-negative on the interval 0, 1. It's also 0 at 1, actually. What can you say about it? Well, there is one thing that if alpha prime of 0 alpha prime of 0 is what? If it's non-negative, 0, 0, then at 0 it can only grow, right? So alpha prime of 0 is non-negative. So this is the first observation we can make, that alpha prime is non-negative. If you have a concavity principle, right? So this is something that I like to refer to as concavity principle. Then alpha prime is non-negative. Now, secondly, what do we know about concave functions? Can somebody tell me?
If
So
they
if you
have
have a function,
local maximum, then they have global maximum.
absolutely correct. If they have local maximum, they have global maximum. But what do we know about convex functions if they're differentiable? So if f is convex and twice differentiable,
The tangent lines are above the graph.
the tangent lines are always exactly above the graph. What do we know about the second derivative of f?
It's not positive.
Exactly, f prime is non-positive, right? Think about a typical example, minus x squared, let's say, f double prime is -2. Second derivative is non-positive, so this is equivalent to the statement that f is convex. Function is convex. So this would be the definition of convexity, but another definition is second derivative is negative, assuming that it's differentiable, right? So with that in mind, you can see that second derivative of f would be negative, or actually it's the same as to say that alpha double prime of 0 is negative. Because if you look at the sort of tail part of alpha here, it depends on t linearly. So if you take second derivative, it disappears. So it's just the same as to say that second derivative of the functional, right? It's the same as second derivative of f itself. Cool. So if you have a concavity principle, that's what I'm saying. Something like Minkowski, something like Prekopa-Landler inequality. We have two things that we can deduce. Alpha prime of 0 is non-negative, and alpha double prime of 0 is non-positive. And the idea is that from inequalities like this, like Prekopa-Landler, for example, or Minkowski, or we will hopefully see more, you can derive new inequalities, right? So basically concavity principles. So one quick example about Minkowski before we move on with Prekopa, something that hopefully you discussed yesterday in your session, right, as was agreed. So if you have, and well, we briefly discussed in class as well. So Minkowski inequality tells us that logarithm of the volume is concave in Minkowski addition of set, right? So my functional f here is sort of logarithm of a volume of a set, and the linear space is Minkowski addition of sets. And if we consider this alpha of t, which is log of the volume of tk plus 1 minus t L minus t log volume of k minus 1 minus t log volume of L. So we take, so because of what we said, notice that alpha prime of 0 is non-negative. what does this amount to? Well, it amounts to exactly what we discussed with you in class yesterday, right? So in the case when L is just a ball, just one moment, maybe K. In the case when K here is a Euclidean ball, then this just amounts to isoperimetric inequality. That we discussed with you. And we briefly discussed, and we discussed with Stephanie, in general, there is this anisotropic isoperimetric inequality or Minkowski first inequality. Minkowski's first inequality. Let's limit ourselves to convex sets. Here, so suppose K and L are convex bodies. We can define mixed volume of K and L to be the lim inf when epsilon goes to 0 of the volume of K plus epsilon L minus K over epsilon. So as we discussed, we have set K and we sort of move the set L around it, create an annulus with respect to set L rather than respect Euclidean ball and divide by the width of the annulus. This is our sort of anisotropic perimeter. Actually, standard definition here also is scaled by the factor of n, 1 over n, just out of convenience, one. So the Minkowski's first inequality tells you that V1 of KL is bigger than or equal to the volume of K to the power n minus 1 over n times the volume of L to the power 1 over n. So this is the version of, more general version of isoperimetric inequality, and I'm claiming without, it's clear from many things in the course, that this statement is precisely this statement, alpha prime. And there is also some second derivative version which we will not dwell on. Maybe you'll discuss with Stephanie again. Any questions about this? So now our goal is to recall Landler inequality as a concavity principle. So how to understand the Prekopa-Landler inequality as a concavity principle. So Prekopa-Landler inequality tells us that if we have a triplet of functions satisfying this condition, then integral of e to the power minus h is bigger than integral of e to the power minus f to the power lambda, integral of e to the power minus g to the power 1 minus lambda. Now, what is sort of, so let's first of all limit ourselves to log concave functions, right? So from here on, for safety and simplicity, suppose that f and g are log concave. What is the optimal h? What is the biggest possible h to satisfy star? Well, we can literally define it to be optimal. Let's actually just literally define it to be optimal. What's going on again with my pencil? Let's define. It's called inf convolution. Of f and g. So f t g at the point z, so this is a function that's defined as infimum of this whole quantity that's written here on the right. I want to switch for lambda equal to 1 minus t for a moment. I'm going to be jumping between these two notations sometimes. Infimum of 1 minus t, f of x plus t, g of y, such that 1 minus t x plus ty equal to z. So this is how we define our inf convolution with index t. And so the point is that inf convolution satisfies the Prikop assumption by its definition. Right, so f box dg at the point 1 minus tx plus t y is bigger than or equal to f of x to the power 1 minus t, g of y to the power t. Sorry, no, not like this, of course. 1 minus t f of x plus t g of y. Right? By definition, we defined it like this. That's firstly, and secondly, f hat tg is sort of smallest possible. We take the smallest possible envelope of such functions to satisfy it. So Prikop-Lendler inequality tells us that for any pair of functions, log concave for safety, integral of e to the power minus this inf convolution is bigger than or equal to integral of e to the power minus f to the power t, integral of e to the power minus g to the power 1 minus t. So here we already see Prikop as some kind of concavity principle. You can view this inf convolution as an interpolation. So it's function that interpolates between f and g as t changes between 0 and 1, right? Because you see that f box 0g is just f box 1g, sorry, is just g, and you get all the stuff in between. So this is almost what we want. Almost what we want. We just want to find a transform. Let's call it tau, such that tau of normal, usual linear addition of functions is precisely this inf convolution. So we need to find the transform that linearizes inf convolution. Because we want the concavity principle in terms of the usual normal linear structure of the space of function. Does this make sense, what I'm saying? So let's consider an example, actually. And this is an example that's very crucial to us. Suppose f of x is what is called an infinity characteristic function of a convex set K. Which is equal to 0 if the point is in K, and infinity if the point is not in K. For this purpose, we will consider, by the way, functions that take value infinity. It's much more convenient this way. So it's 0 on a set, infinity everywhere else. Let's look at inf convolution of the sets KNL. Let's say this parameter what half. It's infimum over all x and y such that x plus y over 2 equal to z of infinity set of k plus infinity. This guy, right? This is exactly what we do here over 2. What do you think it equals to? Can somebody tell me? Let me give you a minute to think.
Indicator K union L.
Indicator of almost, not union. See, we have addition of vectors here, x plus y over 2 equal to z. Right, so addition of vectors.
Minkowski sum.
Exactly, Minkowski sum. Minkowski sum, exactly. Infinity characteristic function of the Minkowski sum. Exactly, so this is just one example that in convolution of infinity characteristic function of convex sets is the infinity characteristic function of a sum. So if you want a functional that linearizes in convolution, we need to understand what quantity, what parameter of a convex set actually adds if we consider Minkowski sum. Let me introduce the following definition of a support function, which maybe Stephanie already introduced. Support function of a convex body. Hk of x is a supremum over y in Rn of x, y in k of x, y. Support function for convex body k. It can also be written as if k is symmetric. Let me write it in a different color. Here, if k is symmetric. This can also be written as Minkowski functional of you who know what k-polar is and what Minkowski functional is. It's a norm. It's just a norm such that k-polar is a unit pole of that norm. So in other words, support function is just a dual norm associated with the convex set k. But of this is not important. One thing things hk is convex function. That's one homogeneous. So it looks like this sort of thing, like a conus. And h of k plus l equals to hk plus hl. So it's precisely the function that adds when we add convex bodies. So in other words, our transform, we want to be such that we want our transform T to take infinity characteristic function of a set into its support function. So basically, this is all just some kind of insinuations. Let's now finally define the desired transform. Are there any questions so far? So the transform that we will talk about that's very important here is called the Legendre transform. I will define it and explain what we mean, and that's where we will wrap up, of course. So Legendre transform is defined as follows. So suppose f on Rn into R is a function. F star, its Legendre transform of x is defined as supremum over y in Rn of x, y minus f of y. This is definition of so-called in a bit more detail and discuss some of its properties, but finally let me explain the most important, the reason why I want to study it is that the following claim, if I consider inf convolution of a functions f and g, take their inf convolution, and then I transform, then this is going to be simply the average of Legendre transforms. So this indeed linearizes in convolution as we wanted. And so hence, therefore, here is a reformulation of the Prokop-Lendler inequality. Integral of e to the power minus 1 minus t f plus tg star is bigger than or equal to integral of e to the power minus f star to the power t times e to the power minus g star to the power 1 minus t. So this is sort of this reformulation of Prokop-Lendler inequality as a concavity principle. In other words, logarithm of integral of e to the power minus f star is concave. So this is a very simple way to formulate Prokop-Lendler inequality. So the logarithm of e to the power minus f star is concave. Final remark before we finish, let me just mention that actually Hölder's inequality, classical Hölder's inequality from analysis, tells us that logarithm of e to the power minus f without the star is convex. So in a way, Prokop-Lendler can be viewed as a dual formulation of Hölder inequality, which tells us that log of e to the power minus f star is a concave functional on the space of functions. So therefore, if you want to do all these linearizations that we discussed earlier, if you want to derive new inequalities from Prokop-Lendler inequality as a concavity principle, take derivatives of alpha. Remember here we discussed here alpha prime, alpha double prime. We need to understand how to take derivatives under Legendre transform. And basically just need to understand what kind of beast is this whole Legendre transform. And all of these things we will do on Friday. Are there any questions? So on Friday, we will understand a little bit Legendre transform, understand how to take derivatives of this concavity principle, which is Prokop, derive new interesting inequalities, maybe understand some more general concepts as well.